Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I'd like to get started. Good morning, Monday morning. Thanks to everybody for coming. It's my great pleasure to introduce Professor Amir Prunelli today to give a talk to you. He's mainly known for the introduction of temporal logic into computer science and his work on the application of temporal logic and similar formalisms for the specification and verification of reactive systems. Professor Prunelli is the 1996 recipient of the ACM Turing Award for seminal work introducing temporal logic into computer science and for outstanding contributions to program and system verification. And in 2007, he was nominated as an ACM Fellow. Since 1999, Professor Prunelli has been a professor of computer science at the Courant Institute of Mathematical Sciences at New York University. And today he's going to tell us a little bit more about combining abstraction and liveness.
Well, thank you very much, Tom, for the introduction as well as for the invitation. I always heard there was something like Microsoft Research, but I never believed it. So this is a good opportunity for me to find out that actually there is all this exciting and interesting work going on there. I'll be staying here most of the week, and I hope to meet personally some of you, and will be happy to discuss any of the things. Now, I listed for this work, this is actually, some of you may have heard me talk about fragments of these ideas, because this is actually an ongoing project for me that has started around 99, maybe even 98. And most of the theoretical work has been done with Yonit Kesten, who used to be my PhD student, of course now is a researcher by their own, and Itai, and who was my student up to just graduated, and Linor joined in for the ride in the last 2 years also. And the whole idea was to try and really explore the relations between abstraction and deductive verification, which has been my field of interest in verification for very long, and actually try to establish that in some sense they are equivalent in proving power and certainly in expressive power, and yet perhaps abstraction will give us a little more, and we'll try to say something about what more it can give us. Okay, so let me start with the general idea, and that is using abstraction for verification. And I'm intentionally listing something which are probably obvious to all of you, but they are useful in order to motivate some of the differences between other very similar approaches to abstraction. So the motivation, the main motivation that we are interested in is to use abstraction in order to simplify and make more effective the process of verification. So what is the idea? Suppose we have a system which is too complex to try and verify directly by any other mean. Could be, for example, infinite state, so you cannot model check it, and even trying to apply deductive verification, which is universal and complete, but yet is not always easy to apply directly. So in order to make the task simpler, you can always try to simplify it by abstracting the system. And by abstracting, you are supposed to transform it to something which will be simpler to verify. Usually the direction that the effect of abstracting it is that you add more possible behaviors, executions. So if you see this for the first time, you say, how can you simplify things by adding more computations? Well, you know, the universal system which allows all computation is one of the most trivial to verify whatever properties it has almost no properties at all, but yet it's very simple. So by adding more computations, you do not necessarily make the system more complex. but to anyone in the field, of course, this is an obvious thing. So the idea is we want to abstract the system into an abstracted system, and then we would like to carry out the verification process at the abstract level. And hopefully, if we do things right, we should be able to conclude from the abstract validity the concrete validity. By the way, since we are not that many people around, please feel free to interrupt me and ask questions at any points in which there are things which are either not clear or even too clear. Should I answer that?
Was it our fun?
Yes, yes.
No, thank you.
Should I try this?
You want to have fun?
Hello? I think you got the wrong number. We are in the middle of the lecture. I thought you had a question to ask. There is no Angela here. Yeah, just type checking.
Just to make sure, we're going to unplug that, okay?
No, this is a good, if this thing is broadcast online. Then. Okay. So, of course, this approach is particularly impressive and effective when the abstraction transforms an infinite state system into a finite state one, because then if previously I could not model check, now I can. Now, let's put a little more flesh into it so that we can ask the question in more well-defined terms. So we define the methodology of verification by finitary abstraction. And again, I'm emphasizing that this is going to abstract into a finite state system as follows. We start with a problem that gives us a system. And at present, we don't say how it is represented, but in some effective way, and a property. And when I say property, of course, this is usually specified by an LTL temporal logic formula, but it could be also a simpler property, such as just simple invariance. And then the idea is that when we abstract using some abstraction, which I'm going to define next, of course, the way we look at it, you should abstract both the system and, in general, also the property, because the abstraction may distort or hide some of the concrete variables. And in case the property refers to those variables, you should also do something about the property, because otherwise it makes no sense. So in general, you say, let's use the abstraction alpha in order to abstract both the system and the property. And then, in case this is transformed into a finite state system, or in any other way, try to verify that the abstracted system satisfies the abstracted property. And what we are interested in is to find variants, instantiations of this general methodology that are obviously sound. If they are not sound, then we cannot use this thing. But also it would be nice, and this is what our project has been all about, trying also to establish that the approach will be complete. Namely, whenever a system is valid, a property is valid over a system, you should be able to verify it using this abstraction technique. So this is the general goal in this. And again, it's very important that we abstract both the system and its and the property. Now, of course, the whole idea of abstraction is in many ways inspired by the notion of abstract interpretation by Couzeau and Couzeau from '77. However, there are some small technical differences, and it's only recently that we started to appreciate why these differences occur and what exactly they ensue, what are the implications of those differences. If anyone is interested, we can have a longer discussion at the question section. But just to point out some of the obvious differences, for example, we don't use or need the Galois connection altogether. On the other hand, whenever Patrick Couzeau listens to any of my presentation, he says, yes, but you are very limited. In what sense are we limited? First, the restriction to finite state domains or finite domains is something that he considers a very serious limitation. He also says that our abstraction always induces partitions of the concrete space state, while his general notion does not require that. So there are those differences. Another very significant difference is that his definitions, even though they never say it explicitly, is always that in the abstraction you use over-approximation. Whenever you talk with him, he says, yes, I could do everything also dually with under approximation. The only problem is that, as you'll see, for us, it's very important to use both over approximation and under approximation in the same process. This is central to our approach. So there are those differences, and they are mainly justified by the motivation. The notion of abstract interpretation originally and still is aimed as giving an over approximation of the states, for example, the reachable states or the reachable computation of a system. The fact that you can later use this notion in order to also verify some safety properties is sort of an after effect. But the main purpose, the main motivation for abstract interpretation is to derive an over approximation of the semantics. By definition, it says let's define the semantics by an over approximation. In our case, the main motivation is, as I showed you in the previous slide, to be able to carry out verification in an easier manner. And as a result of these different motivations, there are those technical differences. Okay, so now let's introduce some notations. So let sigma denote the set of states of an. So our model for reactive systems is essentially a transition system where there is fairness built in as part of the system. We also specify fairness. So later I will say a little about what is this thing. So sigma will be the set of concrete states, which could be in general infinite as well. And we introduce an abstraction mapping, which to start with maps individual states, concrete states into abstract states. And we say that alpha is finitary if the abstract domain is finite. And usually we represent abstraction mapping by a particular syntax, which is a set of equations that defines values of abstract variables in terms of expressions, concrete expressions over the concrete variables. So that means that whenever I have a concrete state, I know, of course, the values of the concrete variables, and then I can compute those expressions, and this immediately gives me the values of the abstract states. So we'll sometimes write this as a list, sometimes as just a vector notation. And the set of these abstract variables is called V of A, the abstract set of variables. Okay, now this mapping will tell us how to map an individual state. However, whenever you talk about properties as well as about the representation of the system, a central element is assertions. My name for assertion is, I use the term assertion to describe any first order non-temporal in particular. When I say assertion, I mean non-temporal. There are no temporal operators in it. So suppose, so now the question is how do I lift an abstraction mapping which originally just maps individual states into assertions, a mapping of assertions. Now, of course, anyone who is familiar with abstract interpretation has a very natural solution. What do you mean? An assertion, always the semantics of an assertion is a concrete assertion, is a set of concrete states. You just map all these concrete states into abstract states, and that should be your mapping. But this is not the only possibility. And as a matter of fact, I am listing here two dual approaches, which are respectively associated with the notion of an over-approximation of an assertion as well as an under-approximation. So over-approximation, also could be called expanding alpha abstraction induced by alpha, is the usual thing, which says, let's look at the semantic notation. It says the abstract version of this assertion, the lifted abstract version in the over-approximation sense, is to abstract each of the individual state and take all of them together. So this contains all the abstract states which have at least one source, one concrete state mapping into this abstract state that satisfy P. Dually, we can also define an under-approximation, which can also be called a contracting abstraction. If you want to express it in terms of quantifiers and mappings, this is the way you can express the over-approximation, and this is the way that you can express under-approximation. Here you say there exists at least one concrete state that maps into P. The mapping is expressed by this. And this one says for all sources of this particular abstract state, we want all of them to satisfy P. So this is why this is called contracting, because if you then look at the abstracted thing and you take back all the sources, you'll get an under approximation, a substate. In order to clarify perhaps this difference, let me draw a picture. So suppose this is the set, this external oval is the set of all concrete states. And of course, when you abstract them into abstract states, then there are, let's assume that this parallelepiped or lozenges, diamonds, group together all concrete states which map into a single abstract state. So you can look at this diagram and you say each of these diamonds corresponds to one single abstract state. And suppose we have a concrete assertion which is not necessarily supposed to respect the partition of the concrete state space inspired by the abstraction alpha. So it may cut some of those diamonds in the middle. Now, the abstracted, in the abstract sense, you must always take an integral number of those diamonds, because these are the abstract states. So in the over approximation, in the expanding abstraction, you take each of those diamonds if it has a non-empty intersection with the ellipse that defines the concrete state. So this is the over approximation, or expanding. Sorry. The under approximation is you take only those diamonds, green in this picture, which are completely contained within this ellipse. So you see there is a difference, usually the border cases. The border cases should not belong to the contracting and always belong to the expanding. Now, in some cases, the original P does respect the equivalence relation induced by the abstraction. In that case, we say that the abstraction alpha is precise with respect to the assertion P. So this is a relation that some special P's will always naturally take an integral number of diamonds. For such assertions, we have the happy situation that the over approximation is equal to the under approximation because both of them take the same set of diamonds. Yes?
Probably very usual case when under approximation and over approximation are very much apart. Almost every diamond is cut. So in this connection, is there any sense to look at middle weight, say, some measure or with respect to some filter?
No. As a matter of fact, for a long while, I was really puzzling why nobody who does abstraction with verification was ever faced with this problem that you should use under approximation for the property. Well, I didn't get to that, but I will get to that. And the only answer that I can give is that if you look at the type of properties that usually people would like to model check, let's say, with abstraction, they are always precise, naturally precise. In particular, most of the properties have to do only with the program counters. So reachability, you say this location is reachable. And in most of the abstraction, when you do an abstraction, you usually abstract the data. But for the control, your equation says the program counter in the abstract program is exactly the same. So you have an identity. Whenever you have an identity, then this abstraction is going to be precise. So it just happens by accident that in most of the application of usually abstraction in the context of verification, they happen to be precise. But I will immediately show you some trivial examples will show you that it will be a big mistake in general to take over approximation of the property. So we'll get to that. Yes?
Yeah, I think generally in abstract interpretation, people don't think of, I mean, the property somehow, like you said, is sort of just implicit. There's
Yes.
Explicit notion of the abstraction precision with respect to the property. It's usually relative to your concrete semantics, and you hope that
I wasn't puzzled about why in abstract interpretation people don't use it. But if you look, for example, at the works of Ed Clark and other people, they always say, well, you abstract and then you test, you model check. They didn't say anything about abstracting the property. And my explanation for that is that it usually happened to be that the properties that usually people verified in that context were precise. Okay, so let me just give you a recipe for a sound joint abstraction. So suppose you have an arbitrary alpha. And by the way, this slide about soundness is not restricted to finitary, just any abstraction. As long as the abstraction is inspired or is defined by having this set of equalities, and it need not to be a finite state necessarily, the abstract domain, then this thing holds. So, well, okay. So in general, there is a question, how do we intend to abstract the property? The property in general will be a temporal formula. So a temporal formula has temporal operators, of course. And without loss of generality, let's assume that it is in positive normal form, which means negations only appear inside. So if you have an arbitrary temporal LTL property, then we say that given an abstraction alpha, we denote by psi of alpha, you leave all the temporal operators along, you don't mess with them, but you go inside to the sub-formulas, which are assertions, and to them you apply under approximation. So this is the way we define psi of alpha, take an arbitrary LTL formula, look inside to the assertions, to the first order sub-formula, and for them you should abstract each of them individually using the under approximation. Now in general, this is my first and only definition of what an FDS would look like. So in general, let me remind you, in case you are not familiar with this notation, we have some finite state set of system variables. We have an assertion theta, which characterizes, so this is a first order formula, which characterizes all the initial states. We have a bi assertion. This is assertion over two copies of the state variables, which expresses a transition relation. And then we have two sets of fairness requirement. This is weak fairness, called also justice, and this is strong fairness, which is also called compassion. And in general, J is a set of assertions, and the weak fairness requires that each of them holds infinitely often over every computation. The compassion, strong fairness, is a set of pairs having sort of a precondition and a postcondition, and the requirement of strong fairness requires that in any computation, if the computation has infinitely many p states, then it should also have infinitely many q states. So this is an abstraction of the usual notion that if a certain transition is enabled infinitely often, then it should be taken infinitely often. Now, how do we abstract such a creature? So in general, we say, well, we abstract it given an alpha abstraction, an abstraction, state abstraction alpha. We abstract it into this abstracted system, where now we say, how do we derive each of the components? So of course, the abstract states are all those which are defined in the abstraction mapping. And then the initial conditions are over-approximated, are abstracted in an expanding way. For the transition relation, which has two copies, both unprimed and primed, you abstract it twice, but in an expanding way. So you just apply this. Well, this is the way you know from abstract interpretation. The transition relation is abstracted by it holding between two abstract states such that they have two respective sources which are connected by a concrete. And then for the fairness requirements, we abstract them individually. So for justice, there is a set of things, so you abstract each of them in an expanding way. Now the only catch, which is a little different, exception, is for the strong fairness. Because in strong fairness, almost by the way I described it, there is an implied implication. Because you say if infinitely often p, then infinitely often q, so there is an extra negation thrown in. This is why you should apply a contracting, an under approximation to p and over approximation to q. As a matter of fact, this is just to remind you that actually the under approximation is a dual of the over approximation. One of them has existential quantifier, the other has universal, and it's almost like doing this dualization. Okay, so this is our recipe for how to abstract an FDS by an abstraction alpha. And we already say how you abstract the temporal formula property psi. And then there is a general claim of soundness, which says as long as you follow this recipe for an arbitrary alpha, we don't care how those expressions are defined, as long as they are defined, non-temporally, just by state expressions. Then if alpha is an abstraction mapping and d and psi are abstracted according to this recipe, then the abstraction is sound. Namely, if you verify that the abstracted property is valid of the abstracted system, then always you can safely conclude that the concrete property is valid over the system. And let me try to illustrate this by a very trivial situation. So this is a very stupid program, non-concurrent, just a sequential program, which keeps counting. It starts with y being declared as an integer with initial value 0, and then as long as y is non-negative, which it will be forever in this case, we just keep incrementing y by 1. Now assume that we want to verify the property, which is not an invariance property, already a temporal property, which says, well, this program has the property that eventually y will become positive and remain positive for the rest of the computation. Now certainly you will agree with me that this is a valid property of this program. The only state in which y is not strictly positive is initially, and eventually we will do the first step from which position on y will be positive. So we would like to verify this for this program. Now this program, trivial as it is already an infinite state program because it goes through all the natural numbers. Okay, so let's do an abstraction which will have, instead of the infinite domain value of y, which is all the integers, including negative numbers, values, even though this program never reaches a negative value. So let's assume, let's agree that we are going to represent it by this abstract variable, capital Y, which has only 3 values, -1, 0, and plus. And the abstraction mapping is so-called sign abstraction. We just look at small y. It can be negative, 0, or positive. And the only thing that we preserve in the abstraction is the sign. So this is how you map an individual y value of small y into an abstract value. Okay? So now let's apply this recipe for abstraction for this program. And rather than show you what is the FDS for that, in many cases you can do the abstraction directly on the program itself by just abstracting all the predicates and abstracting also all the assignments individually. So you can do it statement by statement, which makes it a little easier to apply. So if we do that, this is what we get. So this is what happens to the program. So instead of small y that was declared to be of type integer, we have now a capital Y, which has an enumerated type, only those 3 values, -1, 0, +1. Initially, we have now to translate, to abstract the initial condition, which we do by over-approximation. So in this case, actually, it is precise, because the old initial value was small y is equal to 0, and that predicate is precise with respect to sign abstraction. So we can have initially y equals 0. Now, control, we didn't even say how we map it, but we usually, in such programs, the control is mapped precisely. So we have the same amount of, the same number and same values of locations. Now, the while condition used to be small y greater or equal than 0. And this is also precisely abstracted into capital Y belonging to, could have actually said greater or equal to 0, or saying it's either 0 or 1. The only thing where we have to really over-approximate, and this is not precise, is in the assignment. So in the assignment, we have to check, and this is something that can be done purely mechanically, this is the result that we get. So we ask ourselves, how should we translate in the best way we can the fact that y gets to be y plus 1 without assuming anything about invariance. So in the program itself, we know that once you are in the loop, then y should be non-negative. But let's ignore this fact. We are not allowed to do this. So y, small y in general, could be an arbitrary integer, including negative. So we say, well, okay, we make this a case splitting. If capital Y is minus 1, that means that the original small y was negative. Now, when it was negative, we still cannot predict precisely what will be the sign of y plus 1. Why? Because if small y was minus 1, you add 1 to it, you get 0. If it was any value smaller than minus 1, if you add 1 to it, you get minus negative value. So the best way we can approximate this is to say if capital Y is minus 1, representing in the concrete world negative small y, then non-deterministically, that's the way it is expressed here, the new value of capital Y could be either negative or 0. So we say choose non-deterministically. I'm using here braces to denote non-deterministical choice. In all other two cases, when capital Y was either 0 or positive, then after you add 1, you certainly get a positive value. So this is deterministic, and we get plus 1. So you see that this is a case where most of the things were translated precisely, but the transition relation was not. As a matter of fact, there are rare cases, and they are usually not useful when everything is translated precisely, because if everything is translated precisely, usually you are not abstracting away anything. So usually you will find some imprecision, and that imprecision in most cases will be in the transition relation. Okay, now let's abstract the property. And we say when you abstract the temporal property, the temporal operators are transparent. And what you do, you take all the data dependencies or the assertions inside, the nested assertions, and you under-approximate them. In this case, under-approximating y greater than 0 is also precise, and it gives you eventually y is equal to plus 1. So now you got a finite state program with a finite propositional, can be represented propositional temporal property, and it's not difficult to model check this property over Z, and you'll find out that indeed this is valid. So the abstracted version does satisfy this, from which we can safely infer that this thing is okay. Okay, so this is the good news. Now let's take a case where we have no conclusions. So suppose instead of taking the same trivial program, suppose instead of proving this other property, we wanted to prove or to examine this property. So this property is an invariance property, and it says always small y is bounded, upper bounded by 10. Actually it says a little more, but let's look at this. Now if I try to follow the recipe, the safe recipe, again I have to under-approximate this thing. When you under-approximate this assertion, there are finitely many possibilities. So we can certainly take capital Y to be 0 as belonging to the under-approximation of Z. But y, capital Y equal 1 is not, because there are some positive integers which do not satisfy this. So when you do under-approximation, you remain with this. So what is wrong with this? If you now try to model check this, you find that actually this property does not hold. So this is a situation where the verification failed. However, our soundness only implied that if things are valid, then we can safely conclude that they are also valid in the concrete world. Nothing about counterexamples. So this is usually when you try to do counterexample guided refinement and so on. But at least we are safe here that we did not succeed in proving a false assumption. On the other hand, let me just illustrate to you with the same property that if we were not using under-approximation, but the abstract interpretation guideline of, say, abstract over-approximate everything, then if you over-approximate this property, you get this property, that capital Y is 0, 1, because Y equal 1 has some sources, not all of them, some sources which satisfy this, of course. Y equal 2 satisfy this. Now if you model check increase of alpha with this thing, you'll find that this is sound. So it's only because we under-approximate the property that our abstraction method is sound, even for simple cases like this. Okay, of course this does not prove anything, but it just shows that gives additional evidence. Okay, now the only examples that I showed you, and in many cases when people see abstraction for the first time, usually the way you try to explain abstraction is you say, well, you take some infinite state variables and you abstract them individually. Each of the concrete variables you abstract into an abstract variable, such as take an integer and abstract it by sign abstraction, and so on. But this is not the most powerful way, and as a matter of fact, this is certainly not the place where I should preach predicate abstraction. Let's just say what is the general idea of predicate abstraction. So suppose we look at the concrete program and we identify, so we don't want to abstract always structure the abstraction based on existing concrete variables. In many cases, we say, let's forget about the concrete variables or the partition of the state space of the concrete program into concrete variables. Let's instead restructure it according to interesting properties. So we start by looking perhaps at a concrete program, and we say, well, we can identify some concrete expressions and predicates, which seems to be, some of them can come from the program, the others can come from the property. And we say, well, it seems that those are relevant to the property we have at hand. And you can err in the direction of getting too many of them. The only thing that it will cost you is some efficiency. But you cannot make an error by putting too many of them. So we refer to this set as a predicate base. And now what we decide to do is have in the abstract state domain, again, a finite domain, but having as many Boolean variables as there are those predicates. And the defining equations for the predicate, for the abstraction will be is that whenever the concrete state satisfy assertion predicate P1, then we want B of P1 to be true. So B of P1 is true if and only if P1 holds over the concrete state, and so is for the rest. Okay, so this is going to be our abstract domain. So let me illustrate this on one of the interesting examples where this really is impressive, because it takes a system which is not so trivial, at least deductively, to verify. It's an infinite state system, yet predicate abstraction handles it very elegantly. So this is a special case of the bakery algorithm by Lamport, scaled down to just two processes. And we have two integer variables. Well, actually, they can be declared as natural. They are never supposed to be negative. And they are corresponding, in case you are familiar with the bakery algorithm, to the tickets that each process has. And at any point, whenever, so this is a mutual exclusion algorithm, whenever a process gets out of the non-critical, it should draw a new value for its ticket, which is guaranteed to be bigger than the values of all the others. So it does y1 gets y2 plus 1. Because in this case, there are only two processes, so I have to look at the number of the ticket of the other, and I increase this. And then the access right to the critical section is I enter my critical section if and only if I find that the ticket of the other is 0. This usually will signify that my competitor is not interested, or my ticket is lower than his, because that usually will mean that he drew his value after me, because he drew y2 to be bigger than y1. In that case, I enter, and then when I'm going out, I zero my, okay, so this is the other. So now you may look at this program and say, okay, which predicates seems to be relevant? And in this case, we are not influenced by the property, just looking at the program itself. So by looking at the initial condition, we find, and as well as this assertion, this assignment, we find out that it seems to be important for us, for this program, whether y1 is 0 or whether y2 is 0. So let's agree. Let me also list the properties that we would like to prove. So we would like to verify both safety property of mutual exclusion, these two processes are never at their critical section at the same time, as well as a liveness property, which says whenever process number 1 in this case gets to L2, then eventually it will get to L4. So here we would like to apply predicate abstraction in order to verify those two properties. And the first thing that we should find out is what are the relevant predicates. So it seems that it's relevant whether y1 is 0 and whether y2 is 0. And the only other thing that seems to be important is this predicate which says y1 is smaller than y2. Now, if you were very careful, you probably should have complained, why is this program not symmetric? Why is this test different from this one? And the only reason for that, actually the program also works if we put here y2 strictly smaller than y1. And the only reason that I make it like this is so that this thing will be the negation of this one. So it will decrease the number of relevant predicates. So I'll have only to care about whether y1 is 0 or y2 is 0, or whether y1 is strictly smaller than y2, and this is the negation of that predicate. So I'll need only 3 predicates. Okay, so indeed we choose those 3 predicates. Yeah.
Will it really work?
What?
If
Sure.
it's all symmetric, suppose they do synchronous.
They cannot. An underlying assumption, going back to Dijkstra, is interleaving. Concurrency is interleaving. We can spend 2 hours arguing about that, but that's the assumption here. Yes. Okay. So in this case, we have 3 Boolean variables corresponding to those 3 predicates. And now you do the abstraction, and again, you can do it with the same program, just abstracting the things. And this really is a very elegant example because almost everything here is precise. Including the transition relation, I think. Well, anyway, so this is the abstraction. And the abstraction structurally looks exactly the same. And everything works just with those Boolean variables. And now we can, of course, this is a finite state program. And by the way, the original program, it's actually an intriguing program because this is a very simple program. We have only those 2 integer variables. For a long time, people try to improve the program and make sure that y1 and y2 will be bounded. Nobody yet succeeded. It's still an open problem. And I think that there are some evidence which says that actually you cannot do this. There will always be computation in which y1 and y2 will assume arbitrarily high values. So it's a bona fide infinite state system. And this predicate abstraction reduced it to finite state. Now we can take the 2 properties. In this case, the properties were again relating only to locations, so they were precise. And we can model check it, and we find out that both the safety and the liveness properties held in the abstracted version, and therefore they now hold in the concrete version. Okay, so this seems very nice. We have been successful in those few examples that I showed you to prove both safety and liveness, and arbitrary. Seems like it may work on arbitrary LTL formula. So back in around 99, we says, well, we proved soundness. Why don't we go ahead and prove completeness? So in the beginning, it was a little difficult to see how we can handle completeness. So we proved a partial completeness. And we say that this method, the way it is complete for invariance properties. So invariance properties are properties of the form always P. When P is an assertion, as a matter of fact, you can generalize it a little and have all safety properties. So this method is supposed to be complete for all safety properties. And completeness means what? Exactly what I said. That whenever you have an invariance property and an arbitrary, could be infinite state system, such that this property is valid over the D, then there exists a finitary abstraction mapping. As a matter of fact, I'll show you the proof. And the proof shows you that we don't have to have an arbitrary finitary abstraction mapping. It could be predicate abstraction. It could even be predicate abstraction with a single predicate. So there always exists a proof using this abstraction that will verify this thing.
This is
actually a relative completeness theorem, right? Because it depends on the language of predicates that you use for predicate abstraction.
Yes, yes. So, as I told you in the beginning, we wanted to show that this is not worse than deductive verification. So everything is relative to deductive verification. In deductive verification, there is also relative completeness as well. And the completeness there is relative to the expressiveness of the assertion language. For safety, first order is enough. For liveness, you need something more, like transitive closure or ordinals or anything which is more expressive, or fixed point, mu calculus.
Why is first order enough for safety?
Well, I can refer you to our book with Mana, but you can write an assertion which looks very ugly and of course is far from constructive. You cannot, it's not effective, you cannot use it, but you can actually write things like, well, relative to an expressive, a language with concrete interpretations over the integers. So you can write a first order formula over the integers, will formalize the notion of there exists a computation.
But here you have added integers which themselves are not first order.
Yes. So it's relative to those two things. And here we only prove relative to deductive verification. Okay. So let me sketch the proof. And the proof actually reduces the problem from showing it by abstraction to relying on the completeness of deductive verification. So we say, suppose this is an arbitrary FDS with its own transition relation, and we have a certain predicate assertion, and such that this is valid. So of course in completeness you say, let's assume that it's valid. Now let's show that we can prove it using the current method. Now, by the completeness of the deductive verification for proving invariance properties, there is a single rule called the invariance rule, and this is what the deductive rule says. It says whenever P is an invariant of the program, essentially what this rule says, we can strengthen it into an inductive assertion. What is an inductive assertion? Phi. So phi is the strengthening. You know, like in usual mathematical induction, you cannot always prove a certain property directly by induction, but often if you strengthen it, you find something stronger, then it is inductive. It satisfies the induction step, for example. And this is exactly what this rule says. The rule says we want to verify that P is an invariant. We have to invent, this is what makes it deductive verification more difficult, that you have to invent the right thing, but you have to find a strengthening. So phi implying P means that this is strengthening, such that phi is inductive. What does it mean that phi is inductive? The initial condition implies phi, and then phi is preserved by the transition relation. So those two things are sort of induction. So then we know that phi will be true for all reachable states, and then if phi implies P, then P will be true. And the completeness for deductive verification says whenever P is a valid invariant of D, then you can find phi. There exists such phi. And of course, the proof of existence is not constructive because it assumes that P is a valid thing. But anyway, so the situation which is guaranteed by this thing is depicted here. So we have the initial assertion. So this is the set of all states satisfying the initial condition. And then we have P, and phi should be a superset of theta because of that premise, and it should be a subset of P because of that. So this is the relation between those. Furthermore, we know that whenever we apply rho to phi, we get again a state within phi due to this premise. So we suggest a predicate abstraction, a very natural one. It seems that if we already have phi, then phi is the only relevant predicate. So let's do predicate abstraction with this single predicate. So it will lead us to an abstract domain with a single Boolean variable. So this is what the next slide shows us. So let's apply the recipe. So there is a single, in the abstract domain, there is a single abstract variable, B of phi. When we over-approximate B of phi, then in the world of the abstract domain, we have only states which live inside phi and states which live outside phi. Because in the abstract domain, we have B phi holding. So this corresponds to all the concrete states which are inside. And all the negation of this is all the concrete states which are outside. Now, since theta is fully contained with phi, the over approximation of theta, you just go out and try to find the closest separation. And this is B of phi. If you look at the abstraction of rho, the double abstraction, then since we know that phi is closed under rho, that means that if you have a state which satisfies phi, then successor must also satisfy phi. So that means that the abstraction of your transition relation will, well, there are not that many different things that we can write using a single abstract variable. One of the conjuncts will be that one of the situations is if the pre-state satisfies B of phi, because of the closure, then the successor should also satisfy this. And in addition, we don't know what will happen if you give it a state that satisfies the negation of B of phi. Sometimes the successor will be in, sometimes it will be out. And fairness is not relevant here. So altogether, this abstract system is given by this diagram. Initially, we start with a state that satisfies B of phi. Whenever you take a transition that is from a state satisfying B of phi, you must end it again with B of phi. In addition, there may be this other state, but it does not seem to be reachable. Now, how about abstracting the P? For P, we have to under-approximate. So under-approximate is shrink it until you get an integral number of abstract states, and the only shrinking that you can do is to reduce it to B of phi. So the only computation of this thing has is the single computation that starts and have only states with B of phi. And to show that B of phi is an invariant of this is trivial. Okay, so this is a completely trivial example, but it just shows the advantages first of doing an over-approximation of the system and under-approximation of the predicate. Without this, this proof would not work. And also shows that this kind of completeness proof is not very useful because it required for me to find phi. If I know how to find phi, I can do a deductive verification. Okay, so this seems promising. Am I already beyond my... No, we started 10:30? Yes. Okay, so we have...
We have until 12.
Okay. Feel free also to live in the middle. So it seems very promising that we are on the way of proving completeness. And then, very quickly, we found that there are very simple examples in which we cannot use finitary abstraction, no matter how it is defined. No finitary abstraction can verify the termination of this program by abstraction. And if you want a proof of that, first, let's try. So we have this, again, a sequential program. We have y, which is natural. We loop as long as y is different from 0. And inside the loop, we just subtract 1 from y. And we go on forever. You may ask me, why do I need this skip? There is a technical reason for that, but it's not very essential to the termination or non-termination of this program. I just needed a placeholder. So this program certainly terminates. We didn't say anything about the initial value of y, but it actually terminates for all initial values which are natural. Could start with 0 and terminate immediately, or you could start with several milliards and still terminate. Now, let's try one of our sign abstractions and see whether it can work. So let's apply sign abstraction. In this case, since this is defined to be natural, then we'll have only two values, 0 and positive. So this will be abstracted into this domain. And when we do the abstraction, again, there will be this non-deterministic statement. And the non-deterministic statement says, well, if y is positive, then when you subtract 1 from it, you could get either 0 or another positive value. So in the abstraction, this translates to this non-deterministic choice, 0 plus 1. Otherwise, if y was 0 initially, Well, we have to define what does it mean to subtract 1 from a natural number. Let's just extend the function to say 0 minus 1 is 0. So in that case, the abstraction will give us 0. So this is a nice program, finite state one. However, we lost termination. Why did we lose termination? Because this non-deterministic choice allows an adversary scheduler always to choose +1. So obviously, this program has non-divergent computations. So using this abstraction, we didn't manage to do this. Now, if you are an advocate of refinement, you will say, oh, usually this means that there was a property that was valid in the concrete world, but not in the abstract world. That means that our abstraction is at fault. And let's perhaps use the counterexample, whatever that may mean for termination, in order to refine it. Well, if you do that, then the first thing that you find out is that it's very important not only to know when small y is 0, but also when small y is 1. Because then, when you subtract 1, you get 0 and it terminates. So the natural Cigar application of that will say, okay, you have to add to the abstraction also 3 values. So altogether, let capital Y denote not only the fact whether it's 0 or positive, but also when it is equal to 1. Do I do this? No. So if you do that, you'll get an abstraction with 3 values. It still will not terminate. Then Cigar will tell you, oh, what you are missing is 2. And you can imagine yourself adding those things again and again. So you could say, oh, so maybe this sign abstraction at this particular refinement is wrong. Maybe there is another. Okay, so let me give you, without a slide, what is the proof why no finitary abstraction can prove termination of this program. Why? Well, if you have finitary abstraction, you will have still a finite state program. Now, one very interesting property of this program is that it always terminates, but it has arbitrarily long terminating computations. Because if I tell you, does this program has a computation of size 10 milliards? You'll say, no problem. Take the initial value of small y to be 10 milliards plus 1. So whatever big number I give you, you will always find a computation that has it. Now, no finite state computation can reproduce this property. No finite state computation can be such that it always terminates, yet have unboundedly long computations. And the argument is very simple. If you have finite state and it has very long computation, it must contain a cycle. Just go around the cycle forever. So this shows that there is no way to apply finitary. Now you can ask why it's our fault. Why did you use finitary abstraction? Better take Cousin finite interpretation. But we were keen on really having finitary abstraction. Why? Because we were obsessive about showing the connection between this and deductive verification. Now, in deductive verification, you always have finitely many constructs, finitely many premises, and the proof, after all, well, it may contain some very complicated things to prove in first order, but yet the number of steps is always finite. So we insisted that there must be some way to generalize the notion of finitary abstraction in a way that will yield something that will work also for this. Yes?
But Cousin wants his abstract interpreter to terminate, so the same is true.
Yeah, but he has this additional narrowing, widening.
Yeah,
narrowing.
right. I mean, he achieves it via some magic steps, but the point is, in the end, the number of proof steps will be bounded, even though the abstract domain is infinite. So, I mean, we understand that what it's doing is a proof.
Yes. Okay, so I fully agree with you, and as a matter of fact, it's obvious that we have to introduce some trick. The question is which trick to introduce. And he introduced his trick, and Podelsky and then Byron introduces their own trick, and I'm going to introduce my own trick.
But even when he does his trick, he can't prove termination.
Sure, he cannot. Yes.
The trick should be obvious, right? In deductive verification, people reason about this in some solve this finite logical representation?
Yeah, so you're anticipating my next slide.
And we just have to infer it.
Yeah. Now, of course, the trick is, when we say there is a trick, there is always an element of having to invent something. Even in predicate abstraction, the question is how do you invent your predicates? And of course, this is heuristic, and in some sense, this is exactly as my completeness proof showed you. It's like inventing this phi. If you know how to invent a single phi, then it's really a magic. In many cases, you don't know how to invent directly a single phi, but you will invent several. So yeah, so my trick will also include something that will look like an ad hoc, or something that has to be discovered, a heuristic. Well, the problem is undecidable, so no matter what we do, there must be some creative step. Okay, so what is our trick? So our trick says the following. Okay, we wanted to abstract this system. So before we abstract it, well, as in many cases in mathematics, let's make the problem more complicated first. How do we make it more complicated? We say, well, this is not simple enough, or not complicated enough. Let's add one more thing to it, and then abstract the combined thing. The only thing is what is the creature that we add to this thing. And the creature that we add to it is called a progress monitor. And its purpose, it's usually, you may think that the structure of this thing is the inventive, the creative part, but it's not. All of our progress monitors will have essentially the same form, except for a single parameter. So I will identify the parameter, and you have to be creative about that parameter. In this case, the parameter is just a single y. So what does this do? Essentially, by the name its monitor, it's looking over what its neighbor is doing. By the way, this notation is parallel composition, but of the synchronous type. So I answered Yuri, which we said whenever we have normal concurrency, which we denote by two vertical bars that mean interleaving. And this is the usual way we interpret concurrency, multicore and some other things. Here, we really want a product of automata. So this is synchronous parallelism, which says at any point, this system does a single atomic step. And usually, a statement here is a single atomic step. And together, at the same time, this one also does its own step. Now, this one has a very degenerate control structure. The only thing that it does is repeat this statement again and again. The only thing is that it has a little more power than the other, and that is that it can at the same time observe not only the value of the variable before the transition of z, but also after. So it has the liberty, the license to observe both y, which is the value before the transition, as well as the value after the transition, y prime. So what it does is always compare the value before the transition and the value after the transition. It observes the sign, whether the value of y stayed the same, increased or decreased. This will be a three-valued value, -1, 0, or +1. And then this will be assigned to dec. So dec is supposed to be decrement. I always get confused a little. So when is it positive? It's positive when y has decreased. So this means that if you interpret dec as a Boolean saying true, it has decreased. Yes, okay. So dec says when it will be +1 if y has decreased. It will be 0 if y stayed the same. And it will be -1 if y has increased. So this thing just monitors the progress of y, whether y has, how y has changed. Now, in addition, it also has an added compassion requirement. Remember, compassion is a strong fairness. And the strong fairness that it has this extra requirement which says if dec is infinitely often positive, then we require that also it should be infinitely often negative. Now, this fact is actually derived not by any special properties of z, but it is determined by the fact that y has been declared to be natural. So a natural value has an ordering, it has well-founded ordering. A natural value cannot decrease infinitely often without also increasing infinitely often. This compression requirement just encodes technically this requirement. So you could interpret this thing by saying what we do here is convert the fact that y ranges over a well-founded domain into a fairness requirement. And this is really what turns the trick for us, that well-foundedness is lost when you do abstraction, finitary abstraction. My argument from before exactly told you that you lose well-foundedness, because well-foundedness is something that allows unboundedly long sequences of decreasing, but yet it cannot be infinite. So this is captured by strong fairness. In retrospect, this is one of the things that we wanted to capture in the original design of why do we want strong fairness. So we can always add this thing and know that it's going to be a sound requirement based not on whether this program terminates or not, but based on the fact that the type of y is natural. So whenever you have a natural value, you can always add a monitor for y. More general, whenever you have anything that you can identify as a well-founded expression, which it's well-founded because of the types, then you can add a progress monitor for that measure. Yes?
Perhaps you can answer my question. The next slide, my question is, what is wrong with the most obvious solution, which is that you come up with a loop invariant and a ranking function, a measure function whose measure decreases after going through every iteration of the loop. This is the standard way termination proofs are done in classic deductive verification. And then the whole point of inference is to just guess it, right? Just like you were trying to guess loop invariance using predicate abstraction, you're now just going to guess in both the loop invariant and the ranking function. So what I'm not seeing is why do we need to do all this? What does doing all this give us that is not already there in that story?
Nothing. So in some sense, this is essentially what we are doing. You will see immediately that very soon I'll stop telling you about these monitors. But I will have several of them, and in all of them you will have one or more ranking functions here. As a matter of fact, our method is called ranking abstraction. The only place where I have to deviate a little from your naive description is that your setup, mine setup, is for sequential programs where you have a very well-defined loop structure. Our system is mainly aimed at reactive systems where we don't have loop invariants necessarily. Instead, we have program invariants, which are true everywhere. We also have ranking functions, which are supposed to decrease everywhere. So we have to modify a little because we are interested in things which are less well-structured. But of course, if you have a sequential program where those things, then it's easier to find. But essentially, the technique is very similar. But I will introduce one or more technical terms which will show why this is a little better than the general technique of finding ranking measures. Yes?
Since I came in at a casual time, you have to explain me how is the decrement a well-founded measure in this context? So you subtract -1 from 0, and what does that mean?
Well, I think it will be spelled out in the next. Well, first I defined 0 minus 1, since y is natural, to be 0. But you will see this spelled out immediately. If in the next slide you are still not happy, ask me again.
And the compassion requirement says that it's...
Well, the compassion requirement, you should look at this thing as justified independently of this. The only thing which is imported into this is the fact that y is natural. So whatever this does, DEC really tells you what happens to y. Never mind who did it and how. So in case it was a 0 and you subtracted 1 from it, you'll get again 0. So this difference will be 0. But again, the compassion is valid, is sound. Okay.
So can I just make one point?
Sure.
Which is that there are techniques that are sufficient to prove this program terminating without needing to supply a ranking function. They won't work in general because of your claim, but I think that for certain types of programs, you can actually use finite abstraction, and you can use a little extra structure about the system to prove that such things terminate without needing to show the ranking function.
Yeah, I'm sure. Already in the bakery.
Yes.
In the bakery, I proved the termination.
Yes.
I proved liveness.
Yes, that's right.
So yes, in some cases. But remember that the general direction we want. Yeah. Okay. So the first thing that we do with this thing is form the cross product, because since we say this is a synchronous parallel, let's see really what kind of program we get. So when you do that, you can forget about this thing. The only thing which is inherited to this are two things. First, the declaration of this auxiliary new variable, dec, with its own type declaration. Also very important is, of course, the additional compassion requirement, which we put in, but this has been determined by y. And now, to each statement that appears here, we have to add the computation of dec. So as a matter of fact, this is the last time that you see me talking about monitors. Really, what we think about is that you augment this thing with several. It's very important that we allow several. And this is another difference between you, because in sequential programs, at any point, only one ranking measure. Well, that's not even true. But we'll talk about that. For example, what happens is that, okay, the while statement is still a while, but this assignment is now transformed into a multiple value assignment, multiple assignments, where we assign both to y and dec. So we do a y minus 1 as well as assign to dec sign of y minus y prime. Now you can see why did I need the skip, because this is the thing that will actually clear dec in the next statement, because here there is no assignment to y, but there is an assignment to dec, and since y does not change, this will actually assign 0 to dec. So anyway, this can be, again, mechanically done. And now what we are going to do is to do the simplest sign abstraction to this system. Dec we don't have to abstract because this is a finite domain variable, and the control, the program variables are also identically abstracted. So this is the abstraction that we get. And this now can be done completely mechanically using a good theorem prover, let's say. We had the original sign abstraction of 0 and 1. Dec, we have this. We have inherited the compassion requirement. The abstraction of the system now will loop as long as y is plus 1. And then we have here, again, this non-deterministic choice, because, again, what happens to y is unknown. However, whenever we start this thing with y being positive, we know that dec will be assigned plus 1. Because this is not a minus 1. This is a case of positive value. And the reason that we could conclude this is because we did this abstraction jointly. So a very central thing is that we now do a joint abstraction of this whole thing. So we know that this always will be plus 1, because at the same time we know where the small y came from. If we would try to do the abstraction separately and only then cross multiply, we would lose this precision. And the precision is obtained by doing together the abstraction of the variables together with the question what happens to the variable. Okay, so now this is a finite state system, and it terminates. The only thing is that if you ask your model checker closer, what forced you to terminate, you see an adversary scheduler could always still choose this option all the time. So the reason for termination is a little indirect. It's terminated because we have this compassion requirement lurking around, and this compassion requirement says, well, you can choose this branch as long as you can, but not forever. So it's a little strange way of obtaining termination, but it does the same. So now this terminates. So now the question is, how general is this? Well, in this case, we had a very simple ranking function. Yes?
So you actually didn't need that clearing of text.
No. Well, you see, the difficulty here is because I'm insisting on showing you everything at the level of the programs. In fact, when this is implemented, we transform everything into FDSs. And in FDSs is OK. You see, we had a technical problem. I said that with every statement, we add this documentation. And it was not clear what we will do with the while. While is considered for us a statement. We don't have an easy way to show you a programming construct in which we both test for y equal 1 as well as computing DEC. So we said, well, if DEC is 0, then we can omit this thing. So it's just a question of presenting this as a program. That's all. OK, so now I have an even more complicated case. Why is it complicated? It's complicated because this is a situation where the termination, the ranking, is not that something that decreases at all steps, but sometimes it increases. So that means that we have to have a little fancier termination function, a ranking function. And in this case, a ranking function could be the sum of y plus a predicate plus a value which is 1 whenever L2 is true and 0 elsewhere. So this is something which decreases at every point. So this is a known trick to everyone who did the termination or liveness properties for for reactive systems, where
So it means that non-deterministic choice between L1, L2, and L3?
yeah, yes,
But then if it always takes L2,
it decreases by 2. So even if you add 1, altogether every execution.
it's a sequential composition, sorry.
Yeah, yeah.
Yes, yes, yes.
Yeah, this is a sequential program. Okay, so in this case we have to have a fancier function, and then the structure is exactly the same for the monitor. The only thing is that inside the sign you compare not y but delta, and this already shows the general direction of how would you prove completeness, because we also have temporal completeness from the deductive world, which says that whenever a program terminates under arbitrary fairness, there always exists even a single ranking function. It could be very complicated. Okay, so let's not. This led to the following general idea, which is the generalization of our previous method. So let's call this verification by ranking abstraction. And the general method says, well, suppose you want to verify that psi, and now psi could be an arbitrary temporal formula, is d-valid. So we want to check that this is the case. So you can think about progress monitors. So all the progress monitors will essentially be of the same form. They only will be parameterized by different deltas. And we call them progress non-constraining because they are supposed to observe the system, never to interact or influence. And indeed, they each have their own observation variable, the appropriate DEC, and their own compassion requirement. They constrain the computation in the sense that the compassion requirements are supposed to hold throughout. But we say that this is always sound if this is based on well-founded ranking measures. So you can start by adding of all of these monitors, several of them. And then you can choose a finitary state abstraction mapping alpha and calculate this combination. So you abstract this, and then you model check that the abstracted system satisfies the abstracted property, and you wish to safely infer that the concrete program satisfies this. And then we claim that this method enriched by this additional termination measures is complete relative to deductive verification. So we relied on the fact that that is whenever the property is indeed valid over the system, we can find abstraction mapping, and a non-constraining, here we say a single one, and it can be proved that a single one, but this is again an existential. And the constructs alpha and m are derived from the deductive proof. Okay, so theoretically, this sort of concluded our investigation, that we have shown that the abstraction is not less powerful than deduction. Now the only question, is it just deductive verification in disguise, in dressing? Is it just that you really have to do the deductive proof? If this is the case, then theoretically it may be interesting to a few people in the world, but do we get anything? Now, in principle, suppose there was no slam around and no interesting applications of predicate abstractions. If we were to show this completeness theorem for predicate abstraction, then people say, so what is the big deal? What it is that predicate abstraction gives you over just deductive verification. In some sense, the nature of our completeness proof says, well, you have to invent this inductive assertion, the strengthening, and in predicate abstraction, you have to invent the predicates. So what is the advantage of predicate abstraction over deductive verification? And one technical, well, of course, there are those refinement methods and other things, but one thing that I always found very appealing about predicate abstraction is that it is often the case that the real predicate that you know, you don't know it. It's very difficult to guess it precisely, but you often can guess the constituents. And the constituents will be the predicates that you put in the predicate base, and you rely, in some sense, on the model checker, in case you apply a model checker, to find the best Boolean combination of those things that will give you the predicates. So now what we claim is that a very similar and analogous things appear with ranking abstractions. How so? In many cases, and I'll try to illustrate it at least on one case, you can guess or infer, it's not really infer, you can guess the constituents, several ranking functions which are relevant, and again, like predicate abstraction, you never lose anything but efficiency if you include too many of them. But the real ranking function, the unique one, the single one that is predicted by the completeness proof, is sometimes a complicated combination of them. And in case of ranking function, the way you combine them is not by Boolean combinations, but by building tuples, lexicographical tuples. So it's often the case that you may know what are the constituents in the tuples, but not how they are to be arranged into a tuple. And another thing which always happens is that you have to add those predicate expressions, control predicates expressions. You have seen already in my abstraction, in my example, that I used y plus something that depends on the location. And if whenever you want to apply deductive verification, you have to invent those things. So it would be nice if the model checker will give us those. So let's try to illustrate this thing. So this is another sequential program, but even this thing alone is not easy, not completely trivial to verify using strictly deductive verification. So this is a nested loop example. It does nothing interesting, just terminate. But there are two non-deterministic assignments here which allow y and x to be assigned arbitrarily high positive values, and then it has to count down since those things. Furthermore, within the innermost loop, you can assign new values to within the outermost loop, you are allowed to repeatedly assign new values to y, which is the innermost loop. So, for example, it's impossible to give a bound on how long it will take for this program to terminate. So it's not a program that you can prove termination by explicit measures of trying to. Now, if you want to do a deductive termination of this program, well, due to completeness, there should exist a single ranking function, and it is given here. However, you have to really have some experience in the practice of these things to decide that this thing must have 3 lexicographical tuples of size 3, and the expressions should be this combination of expressions using some references to control predicates and so on. So I would consider that to be relatively complex things to do. Now, what we claim is that just looking at this program, so it's almost like the initial heuristic in predicate abstraction. You look at this program and say, what things seems to be relevant for termination? Well, you look at X and Y, and you see that essentially there is a countdown of them. Well, there is an assignment that assigned to them very high values. But since this is heuristic, we can say, well, it stands to reason that X and Y are relevant termination measures. And then the methods of ranking abstraction will allow you to say, okay, let's have, similar to predicate base, we have ranking core. This is the name that we give to a set of expressions that we believe are relevant for proving termination. So we will form a ranking core consisting of X and Y, and then you will apply predicate abstraction, and predicate abstraction will actually abstract this and verify using the fairness requirements that this program always terminates. So this is why I say that there is a very strong analogy between predicate abstraction and this generalization of ranking abstraction, where the main things that you gain are the fact that you can use a set of them, and then the exact arrangement, the model checker is responsible for trying to find out for you the best combination. So let me see. So the ranking abstraction, if the only thing that you say is we believe that X and Y are relevant, do for me ranking abstraction with this core, it will produce this type of thing. This looks terrible, but it's still a finite state program. And it has these 2 extra fairness requirements and these 2 extra variables. And that is enough in order to prove termination. Again, the termination will use fairness in order to verify this thing. Furthermore, we currently have now a way of reconcretizing. In case you are really interested in producing a deductive proof, there is now a way of looking at what the model checker produced and producing something which is equivalent to this terrible thing that we have shown here, and give you something that you can use as a certificate. Okay, I think that I'm going to conclude. So this tries actually to remind you what are the main advantages and features of predicate abstraction. So I think verbally I essentially said most of them. It has a heuristic for initial selection of a predicate base, has a heuristic for refining the abstraction. It does not require the specification of a precise inductive invariant, but let the model checker find it for you. Well, this is what the last bullet says. And what we claim is that there is a very strong analogy where most of these advantages are also present in the application of this ranking abstraction. You give several of them. You have a heuristic for an initial selection. We now have a method for refining the predicate by something like SIGAR. It does not require the specification of a precise global ranking function, but rather will find it for you. So let me just flash the final conclusion for you. So there are some things here about this extraction. So the general idea is that you need some generalization. Finitary abstraction cannot prove all Liveness properties. Here I mainly illustrated uses of these methods for proving termination, But we already know that if you can prove invariance and termination, then you can prove all of temporal logic's properties. So it can actually is now complete. And we would like to encourage people who have been doing predicate abstraction so successfully also to try this notion. Yeah, this last thing is has to be answered. Okay, some time ago, much earlier lecture, I actually said that therefore, in view of this completeness, then abstraction can replace the deduction. And somebody reported to Shankar about this, and Shankar was very upset with me. Said, "Oh, you called on giving up deduction." I say, no, this was reported all wrong to you. I just wanted to show that it is at least as powerful. Okay. So we should not consider abstraction as replacing deduction, but rather as complementing and enhancing, because this notion of it helps you to maybe find the best invariant or the best ranking function, I think is quite an interesting application. And the last thing is never pay too much attention to completeness. Theorems, you are upset when you don't have them, but once you have them, they are nothing. They don't help you very much. At least you know not to search much further. Okay, so thank you very much.